area
Recording in
around
progress.
the railway is actually moving, maybe subsiding. However, it might also be that the track itself remains stable. So, but these are lots of technical details. It's very interesting to look at that, what you're actually measuring, and I hope we have the time at the end to go a bit into some of these details. So the deformation, stability monitoring, linear infrastructure stability monitoring would be what for me comes to mind, and what is very widely used in many countries, but also in China, used generally for many of the high-speed railway, to monitor many of the high-speed railways. Okay, how can I extract a CSV value of the interferogram fringes to be integrated with GNS values? Now, I'm not sure. Okay, what is the CSV value that you're looking at? Because you know, CSV to me means the comma-separated values, so it is some kind of data format where you write out your values separated by comma. Now, I wouldn't know what format you write it out and what are the values of interferogram fringes you're looking at, right? Nevertheless, there are, if you look at interferogram, if you look at, well, let's say you look at motion here, okay, there are several things you need to consider. First, very important is when we do interferometry, we are looking at differences in motion. So we will not get any kind of absolute motion value. Instead, we get an information that tells us this pixel is moving so many millimeters, right? In comparison to another pixel. So one pixel compared to another pixel, that's the information we get. We get a relative motion out of interferometry. So from one pixel to another pixel. So if you want to compare that to any absolute measurement values, you would need to first move towards absolute values, right? That you get things that you actually can compare. So that, I think, would be coming to mind what you may need to do. Right? What you're going to get from interferometry is relative motion or height from one pixel compared to another pixel, not an absolute value. Okay. How can we derive building roof forms using SAR data in case we would have a building footprint and SAR data? Well, honestly, I wouldn't know. Right? I would do that. So, okay, let's say you would say you want to use interferometry for that. I want to get the height information. Now, the main problem that you most probably is facing that you will get two less measurement points typically on your building to really reconstruct the roof form. So if you want to do such roof forms reconstructions from LiDAR data, you're going to have many points on a single roof, so you can actually then start to reconstruct that very well. For SAR data, you would have a limited number of measurements. Depending on the roof structure that you have, you may get even no measurement from the roof directly. So the signal may be reflected away. You may, because you have a side-looking system, you may just only see one side of the roof. That would be rather common. If you would have a gable roof building, you probably just see one side of the roof. Anyway, so that's going to be difficult. Now, if you have high resolution data and only a single star image, you could try to analyze the layover, the shadow, the form of them to derive some information of the building. You may be able, under good circumstances, to reconstruct the roof from there even. If you have, let's say, a limited set of roof forms that you're looking for. So you only have, let's say, a flat roof and a gable roof. Then you may try to, fit them. If you have only a limited set of models, you may try to find a fitting model. Well, that would be possible, I assume, but certainly very, very difficult. And certainly you would need, in any case, a very high resolution data to do that. Okay. How to know if there is uplift or subsidence in the INSA? That's a good question, right? So first of all, we would look at the equation that we have. So in principle, from the measurement principle, we are looking at the line of sight deformation, right? And the line of sight deformation has a sign. It's negative or positive, and typically we define it as positive being moving toward the sensor and negative moving away from the sensor. So if you only look at, if you only suggest it can only be subsidence or uplift, right? You could derive that from the sign of your deformation. You're gonna estimate a deformation, either positive or negative one, right? So you would be able to get that. Now, again, when we look at that equation gives us the difference in the phase, right? But it is the equation itself would be the unwrapped phase, right? What we measure, though, what we get from the sensor is not the unwrapped phase, but the wrapped phase information. Now, from the wrapped phase information, to come to a measurement, we typically do unwrap these phases. And when we unwrap them, right, there's another slide. Okay. I think there's another question coming like that. Okay, when we unwrap them, I will then talk about it again. When we unwrap them, if it's going, in which direction our unwrapping is going might be ambiguous, and we may end up with the wrong sign in our displacement, which would then be at the end an unwrapping error. Right. Now, so where are we? Okay. Now, if we extend your question into, you really want the deformation, and you want to be sure if it's subsidence or uplift or horizontal motion, right? Because we only measure the line of sight deformation, so we only measure in this direction here, right? So we can't really be sure if you're moving down or if you're moving to the east. In that case, if you're moving horizontally, to really make sure out of that, you would need two acquisitions from two different orbits, ideally ascending, descending, and then if you have a line of sight direction from the other side, then you can solve that one and clearly identify if you have a subsidence, an uplift, or horizontal motion, or what is very often the case, a mixture between both. Right. So, but you're going to need to make that for sure is to make sure about it is you're going to have a ascending descending combination. Okay, does the direction of azimuth change in ascending and descending? Well, that's certainly the case. So just to quickly go over that again. So when we have here ascending, our satellite moves in that direction, right? So our azimuth direction, our heading angle would be something like 350 degrees, right? Ascending, okay. And descending, we are going down. Our azimuth direction is something like 190 degrees typically. So yes, the azimuth direction is changing in ascending and descending. Yeah, okay. So I hope that's clear enough. Okay, how to identify the look direction just looking into a star image. Now, I would suggest you not to do it, right? Because that means you don't have the metadata, and then you will not be able to do much with the star information. But anyway, if you want to do that, you best is to identify, for example, a building or another tall object where you can identify the layover direction, right? This would be layover, or the shadow direction, right? This is shadow, okay? So, and then it's rather simple. The layover, right? That building, so it's layover approximately that direction. The layover goes toward the sensor or opposite of your looking direction. So if that's the layover direction, you're going to look in this direction. And similarly, you can look at the shadow. Okay, this is the shadow goes in this direction, right? So the shadow is in the direction of where you're looking. Okay, so if you can clearly identify a shadow or layover, then you can identify the looking direction of your sensor. Okay, so you need to find some building or something topography. This topography so that you can see layover and shadow. Foreshortening could also work, right? If you identify the direction of the foreshortening, and then you can derive the looking direction. Okay. How to know the value of deformation? Is that manually by counting the fringe? Well, ideally no, right? Okay. I wanted to make another picture here also inside. Anyway, I know. So I showed you that by counting the fringe for you in terms of a course, and you can do it manually, right? But otherwise, what we then do is phase unwrapping, right? The same that we use for DM generation, we also use for de-insar. We can unwrap these phases with the phase unwrapping process. And then we get to the unwrap phase, which we would then use to measure the deformation, right? From the unwrap phase, we can then, sorry, I have to go back several slides. If we have the unwrap, sorry, which one? Okay. Yeah, sorry, if we have the unwrap phase, right, after phase unwrapping, because phase unwrapping is successful, right, and we get the unwrap phase here, okay, and then we can directly derive the deformation value here from the unwrap phase again. What you're going to get is you're going to look at the phase difference, right, between 2 points, okay, to derive the, actually the delta D, right, the deformation difference between these 2 points, because you're not going to get an absolute value even after phase unwrapping. because you still don't have the total and absolute number of phase tracks that went through, but you have the difference in that from one starting point in your image to the other pixels in the image. So you're still staying relative to each other. Okay, but after phase unwrapping anyway, you can get the deformation difference between the pixels just from that equation. Right. So the answer again is no, to make it quick and short. Ideally, we are not manually counting them. We are putting it in the phase unwrapper. Okay, and then look at the phase values and transform them with that equation to deformation values or deformation differences. If we, for example, define one reference point in the image, we say that point is 0 deformation. Okay, and then the rest of the image is relative to that point. We can then rather simply derive these values. Okay, right, and the reason why I maybe asked the question is because I went on and on through the course by manually counting that, but more just to, to demonstrate how that would be done, or how the phase unwrapper, what you gotta get at the end. But in practice, you're not very seldomly doing it manually by just counting the fringes. And if you just want to have a rough estimation, it might be faster. Anyway, okay. How to clarify if it's an error or landslide motion? Well, that's good. Good question, right? There's not a good answer for that. So typically, we're gonna have to see that we get a clear enough signal so that we can say, well, that is not, noise. So you have to separate it from noise. There is, well, what kind of error you're gonna have? You have typically, there might be atmospheric error, okay, or DM error. That would be the two errors that play a role here, because just noise, you're gonna separate noise from your clear signal. So let's assume you have a signal, right? Now atmosphere, the atmospheric noise, the atmospheric signal is rather long, okay? So you're gonna have slow changes over the image. While a landslide is typically a rather small area. So it's typically, we are not confusing the landslide. If you only look at the fringes, at this moment I assume you only look at fringes, okay? So typically we are not really assuming the atmosphere, not really confusing the atmosphere with landslide. So the error source where probably is most dangerous in that regard would be the DM error. And that that's there because if you have a landslide, you typically have a relatively steep mountainside. That also means typically your DM is often not fitting as well as it should. So on that side, you may end up with DM errors, and now you need to separate them. That can be challenging, right? That can also be, at the end, by only looking at the fringes, which sometimes you do in that case, you come to the realm of human judgment, right? You're going to have to judge that. So experience plays a role then, and sometimes also like previous knowledge by knowing, well, there is a landslide there. What's a bit an advantage is typically, not always, but typically the DM errors are mostly more related to the top of the mountain range, and the valley, so the misfit is mostly there and not so much on the mountain side itself. So that can help you to separate them. Right? But at the end, it's a case-by-case situation. If you have a very good signal, means if you get very coherent signal, you're gonna see the landslide very, very clear. So the most problem is if you have a rather noisy, incoherent signal to begin with, you may end up a bit in trouble. Anyway, interpreting these fringes for many reasons is not really what we want. Okay, as we come to the human judgment, and we do not like that. Okay, because it's full of errors. Okay, so we'll come and talk today about more methods where we get to numerical values at the end. Okay. All right. If we monitor the movement from glaciers, we're going to have a time series, so we're going to have many images and make, for example, the INSA about that. So now the question is, because we're using the same DEM, right? Can we say that the DEM errors will be eliminated because we are looking at the same scenes with, at the end, the same DEM error, right? But it's not so easy. So if you're looking at the equation here, which gives us here the relation between the difference in height between 2 pixels and the difference in the topographic phase between 2 pixels, right? That's the equation you would need to solve. But the issue is, although your DEM stays the same, your baseline does not, right? Between each image, the baseline is different. So if we solve toward the phase, if you solve toward here delta topo, you will see that even if delta height is the same, so the height error is the same, the perpendicular baseline is not. So the phase that derived from that height error will be different each time because it's each time a different baseline. So you will not be able to just do it like that. However, the baseline is also a known value. And so you can go in there, you can go looking at the difference in baseline and estimating actually the height error. If you have many examples, you can then estimate the height error using that information. If you know the height error, right, if you identify the height error, you can then, because you know the baseline, you can then calculate the topographic phase error and remove it. Right? So that's possible, and that's what we are going to do in PS-INSA. It's one part of PS-INSA in it. But it's not as easy without correction of it. Okay, without correcting it, it will not work because each time you get a different phase. So it's not as easy if you say, well, the topographic phase will always be the same. It isn't, because the baseline is always different. So it's not that simple. Okay. So in coherence, we have a value that we interpret. In interprogram, we have to see directly the image for interpretation. We will not get values. Well, you get values. Okay, you can ideally, for example, unwrap them and then get phase differences between 2 pixels. You can then calculate the deformation difference between these 2 pixels and so on. So that is all true. We were looking at interferograms and interpreting them so far because that's rather common in the INSA. But we're moving away from that now today. So we're moving toward PS-INSA and other multi-baseline methods. So That means methods where we use multiple images to analyze that. And then we move toward getting values, okay, away from interpretation. We do not want that. Okay, we do not want really to interpret these images. We want to have measurement values, right? And we're gonna get them. We're moving there now. Okay. Okay, how to convert the line of sight deformation into actual deformation or 3D deformation? You see, that was the question. Actually, I should have put these two questions together. Right. So I already answered that a bit. What we're gonna have is we have to do that. We need two measurement values, so two stacks, two images from ascending, descending, ideally. Then we can here form a 3D vector of these two measurements and derive the motion in vertical and horizontal direction. And we can actually then also derive a 3D deformation vector. Right. So if we have two measurements, what we then need to do is identify identical points. That's basically a challenging value because you're looking from two different directions. What we typically do is we average over a similar area. So we say, okay, we take the measurements in a certain pixel from the ascending and the measurements in a certain pixel from the descending, and then derive the vector for the values in that pixel area. And then this is it's a rather simple equation. I'm just thinking, I think I don't have the equation on the slide. I think I can put it on some slide on. It's rather simple. And you can look it up to come there to then horizontal and up and down measurements. But what you need is two measurement vectors. Purely theoretically spoken, you could also start to separate if you have like a different orbit direction, but generally from the same direction, right? So two ascending orbits but a different looking angle. You could also start to derive certain. I don't really want to say 3D. It's more like a better than 2D, vector, because you don't have a really good angle to do that, right? But best is ascending, descending, but the pure minimum is that you need two measurement values. Okay. Otherwise, you cannot go from a 1D to a 2-dimensional or even 3-dimensional measurement. Okay. Aside from SRTM, are there any other height data that can be used for hydrological analysis? Right? The data is a bit outdated. Does this have negative impacts on the analysis? Well, I guess if it has a negative impact, that very much depends on your test area, right? If there have been huge changes or not from the time being. But there are other data available, but I can't comment on their quality or on their suitability for hydrological analysis. But you may look at where we have the ASTER DEM. That's some optical data from the ASTER satellite. There is the ALOS DEM that's derived from the Japanese radar system, the ALOS system. You can look at the Tandem X DEM, the 90-meter DEM would be freely available, and the higher resolution data is available for scientific use if you basically write a proposal on that. And now recently, I guess the idea would be to look at it's a Copernicus DEM. I think that's also available now or soon. That's from ESA. You may try to find that. Copernicus DEM, which is also partly based on Tandem and then added with additional data. Yeah, that would come into mind. There are probably more. You can search that, but on their suitability for hydrological analysis, I can't comment on that because this I really do not know. But you might look at them. I think the Copernicus DM is probably the newest one. So try to find that one. Okay. Right. So that has been the questions from last time. Okay, so let's take a look at, I go back a little bit on what we talked last time, just to move into our new topic. Okay, so we were looking at differential interferometry, and differential interferometry we do in the repeat track mode. So that means our satellite is taking an image, right, and then it's coming back at the same orbit, taking a second image, so that we have, for measuring motion, we need a certain time difference, right? A difference in time. Be it satellite or be it airborne, you fly and you come back at a similar position, which, by the way, is much more difficult to do with an airplane than it is with a satellite. But yeah, then you can do the interferometry, which is looking at phase differences anyway, right? But if there's a time difference, we have atmospheric differences, right? So the atmosphere is different. We have a past delay difference through humidity, water vapor content, air pressure, and so on. We see differences in the vegetation, which can lead then to temporal decorrelation, because now we're looking at very different things. Okay, our signal, you see, if you look at this extreme example, okay, our signal gets now reflected somewhere. There's no leaves, so it gets reflected somewhere here, right? And here it gets reflected somewhere more on top. It's a huge difference on the phase center, right? So we're measuring, we're very different points even. You're not measuring the same thing anymore. So your signal is not coherent. That's one of the temporal decorrelation. But what we're interested in differential interferometry is actually this difference in the position, this motion, this deformation. That's for differential INSA what we are looking at. Now, the temporal decorrelation is the main problem that we are facing here. We see after one day. We still have lots of good information from the interferogram, not so much the correlation beside the water area. Okay. But after 15 months, we have most of the area is completely decorrelated. So that means you would not get any useful information anymore. We're just now in the noise. So that is the huge problem if you want to measure motion, the temporal decorrelation. Now, when we are measuring a DEM, we can fix that. We can fix that by taking measurements at the same time, like in the SRTM, for example. We have the transmitting antenna in the shuttle and receiving antenna in the shuttle and another receiving antenna outside of the shuttle. So if we're taking the measurements at the same time, we do not have temporal decorrelation. We have a very, very little temporal decorrelation. I have to say that because actually even for SRTM, the time difference between these two images is not exactly zero. There is a small time difference between them. But anyway, very close to zero, and we have basically no atmospheric differences between these two images. Again, there is small atmospheric differences because their path is not exactly the same. But again, very, very small differences. So we don't really have temporal decorrelation problem and atmospheric problems in that configuration. However, if you're taking the images at the same time, you can't really measure motion. You have to measure motion in the time difference. Otherwise, you can't measure it. So it's not going to work like that for if you're interested in motion. So the problems of atmosphere and temporal decorrelation, that just come back to us again. Right, and I already showed you the slide, the surface motion contribution, right, can be calculated. The phase of that 4 pi divided by the wavelengths times the motion, and that again, that it would be the, sorry, again, that would be here the unwrapped phase, what we actually get. I'm writing so ugly. Okay, what we get is the wrapped phase, right? It's not so easy to paint with the mouse. Okay, right, it's the wrapped phase, that's what we measure. So from minus pi to pi, the wrapped signal, which is not the same, right? It's not the same like this one. This one would be the unwrapped one, but we actually measure the wrapped one. So we need to unwrap that to get there. We need the unwrapped measurement to get to the deformation. So again, the wrapping of the phases needs to be solved also here. If D, or better, right, we're actually looking at delta D. Right? Actually, we're looking at phase difference between 2 points, deformation difference between 2 points. If delta D is very small, right? If it's smaller than the 2 pi, right? Then we do not need to unwrap, right? Because then our measurement, the wrap measurement, would be the same as the unwrap measurement, right? Because it is smaller than 2 pi. In that case, right, for very small motions, we do not need to unwrap and can directly get to the measurement. The problem is, well, we don't really know that, right? Because we only have the wrap measurement. If we just assume they are always small, we are probably underestimating every motion, okay, because they might be wrapped. We're coming back to that over time and quite a lot, but yeah. Right, these are the backgrounds here. Okay, now our INSA, it contains the topography, right, the motion, the atmospheric delay, and noise. It's all together, right, if you want, mixed together in the phase that you get. And plus, right, what would you need to say, the topography, we have the topography phase that would be like an unwrapped phase, the motion phase would be an unwrapped phase, the atmospheric delay would be an unwrapped phase. The noise, not really, doesn't matter. And all of them together gives you the unwrapped phase, but what you measure would be the wrapped part of that. So, again, not so easy to get them from there to the original values. Nevertheless, okay, so if we are interested in motion, then we want to remove the topography, right, and the atmosphere, right, or like here we can try to ignore the atmosphere and the noise, so we can get to the motion. Right, so goal is in that case here to remove the components, to estimate the components, and then remove the components that we're not interested in. And not to forget, the motion that we measure is always in the line of sight direction of the sensor. Right? And then typically the DINSA results, they look something like that. So you have here these pictures that we then try to interpret. We can also measure, like we could, right, in that picture, because you get questions like that. So you could measure the phase value here, right? Phase value here. Yeah. No, sorry. Okay. So another phase value here. Okay, and take the difference between these two phase values. Let's say if you assume that would be the stable point, you can measure what's the difference in motion from here to here. Okay, you see from there to there, there is that's less than a phase cycle, so you wouldn't even need to unwrap it. Okay, if your reference point is somewhere, here to measure to here, well, you're gonna need to unwrap from here to here because there's more than a phase cycle. Okay, but certainly we are not only, even in DINSA, we are not only looking at the beautiful picture and trying to interpret them. We can also measure in them, especially in unwrapped examples, and then go there and get measurement results also from here. Okay. Point is, we are often trying to interpret to see, is that now real deformation, is atmosphere? So that's more of an interpretation question, so that we can, let's say, judge the measurement values that we get, that we can estimate their validity or their meaning, right? But unfortunately, again, in the INSA, we are often in this interpretation phase. We're working in this interpreting images, which is not really what we want, which I also can see from lots of your questions, that you don't really want that. All right, now, again, we have these INSA phase contributions, right? They are important. So when we go to flat interferometric phase, that's that one. We can remove that just by the so-called flattening process. I showed you that talk on INSA. That's relatively easy to do, and typically we can do that easily. Okay. Then we have contribution from elevation, displacement, atmosphere, and noise. Well, noise is hopefully small, because here we talk mostly on thermal noise. So the three main components that we have are the elevation, displacement, and the atmosphere. And you see right, if you want to have the phase information, the phase with respect to a given height difference can be calculated like this. This is the equation. And all the other values are known. We know the incidence angle for each point. We know the range to each pixel, and we know the baseline for each interferogram. Then similar here, we can calculate the phase based on the deformation. We know the wavelengths, so we can get to these values. Okay, so this right. Let me mark these two equations here. The equation of the relation between the difference in height and the elevation phase, right? And here this equation is the difference in deformation and displacement phase. These are two important equations, right, that we're going to need later on for PS-INSA especially. Now, in terms of the atmosphere, we do not have an equation to calculate that. I showed you one, right, when we talked in INSA. We talk about INSA or also such geodesy. You can calculate that delay that is based on weather information like water vapor content, air pressure, temperature, electron content in the ionosphere. So if we would know all these values, we can calculate them. The main problem is we do not know them in the resolution that we would need them. Okay, so we can get these values globally. You can download them. There are different models available also globally, and then you can download them, but the resolution is typically very bad in, it's not that bad actually for global model, but much worse than what we would want with respect to the, the resolution we have in our star systems. So we're not really getting there. Okay, that's the main issue, right? You can calculate that, but we're gonna solve that. We're gonna estimate the atmosphere from the SAR data itself. That's the way that we fix that. Okay, so these are the important phase contributions, especially elevation, displacement, and atmosphere. These are the three main components that we're looking at. All right, that was it. That's where I stopped last time, basically. But there are three more slides in terms of the INSA that I wanted to show you. What we discussed until now, right, is the function that we call the cross-track INSA. Now, but we can also do a long-track INSA that makes a cross-track is, right, but in the looking direction of the sensor, right, transmits, we annotate here. So this is the direction we are looking at. Okay, let's see, a cross-track direction, and the along-track direction is the satellite, is the direction our satellite is flying toward. We can also do interferometry in this direction, right? So what we are measuring are these phase differences, right? So when we, let's say we have here like an X-band system, okay, so our phase wavelength is 3.1 centimeter. In the INSA, we measure a full phase cycle is half the wavelength, so something like 1.5 centimeter. So in our delta t, in our time difference between our two acquisitions, right, we measure things that are ideally below movements that are ideally below 1.5 centimeter, so that we can get them without unwrapping, right? So we are measuring very slow motion, right? If we think about, we have our satellite, okay, Terasa X is going around, comes back to the same place in the same orbit after 11 days. So the speed of things that we measure would be something that measures about a centimeter in 11 days, okay? So very slow motion, all right? So, something that moves in the area of a centimeter or less than a centimeter in these 11 days. So you can estimate what kind of things you can measure. However, if we have a much shorter delta t, if we have a different delta t, then we can measure faster motion. So let's say we have a satellite constellation, right? We have satellite coming back. We have multiple satellites. Let's say we can make an interferogram after 1 day. So now you can measure something that moves about a centimeter a day. We come back after 4 hours. You would be able to measure something that moves a centimeter in 4 hours. You see, then we would move more towards something like we talked about. We had a question about the glacier and the ice, right? If we have such a short revisit time, we could do that better, right? So what we can measure, right, is a relation between our time difference and the wavelengths. Now, if we reduce that time difference even more and make it very short, and we can measure even very fast-moving objects. So you see, we can actually separate. There is experiments done in the SRTM, in the expand SRTM, right? If we separate that antenna from that antenna and take the time difference between them, which is very short, right? But there is a time difference. And then we can look at what is moving centimeter, some millimeter during that short time. Okay. Or the other one is here Terrace X by separating the antenna